So today we will be studying about a new periodic property which is known as ionization potential. Definition says that ionization potential is the amount of energy required to remove a loosely bounded electron from the outermost shell of an isolated atom. Means, okay, suppose this is our atom. Okay, this is nucleus and there are several number of cells. This electron here lies in the outermost cell. So ionization potential explains the amount of energy required to remove a loosely bound electron from the outermost cell of an isolated gaseous atom. Means how much energy is required to remove this electron from the outermost cell. Okay, that is ionization potential. Here it is important to understand few terms. First is isolated gaseous atom. Why is it written as isolated gaseous atom? It's a collection of atom, let's say. If we provide this system with some energy, the energy can either be used to separate the atoms and turn it into an isolated gaseous state, okay, or it can be used to remove electrons. So whatever energy you're providing into the system is being used in two ways. It is either to separate the atom or to separate electrons from the atom. The energy used only for this process where the electrons are being removed from atom is known as ionization potential and not this energy. Is that clear? So we are making an assumption here that our entire system consists of isolated gaseous atom, means all the atoms are separated first, and the energy is only used in removing the electron and not separating the atom. Does that make sense?
Yes, sir.
So when the atom is already in its isolated gaseous state, the amount of energy required to remove that electron is known as ionization potential. So for a fair comparison, we are ensuring that all the atoms have isolated gaseous state, means they are independent from each other. Ionization potential depends on two factors. One is nuclear charge, means the number of positive charge in the nucleus, and atomic size. In fact, atomic size also depends on nuclear charge. So these factors are interconnected. And I also told you in the previous class that atomic size is the main factor. Okay. So most of the periodic property you see later on after this would strongly depend on atomic size and nuclear charge. So these are two of the fundamental periodic property, and the other periodic properties are very related to this. Clear? Okay.
Yes, sir.
So what if there are like more than two atoms? More than two electrons.
Then first, second, third ionization potential.
Okay.
Okay. First ionization potential means how much energy is required to remove the first electron from the outermost cell of an atom in its isolated gaseous state. Second ionization potential means how much energy is required to remove second electron from an atom in its isolated gaseous state, and so on for the third and the fourth ionization potential. Trend in ionization potential. Okay. For, as I said, the trends depend on the atomic size. So ionization potential is compared to atom. One which is bigger in size and the other which is small in size. Okay, being small in size means the outermost cell is more closer to the nucleus, and being bigger in size means the outermost cell is more far away from the nucleus, right? So now just think logically and tell me, see, if this electron tries to sneak out, the only obstruction in the path is the central nucleus, because nucleus is positive charge and it will prevent this electron from sneaking out, right? So actually the energy required to remove this electron is nothing but the energy required to balance the attraction by the nucleus. And it's logical that if this nucleus is far away from the electron, it would be less. If the nucleus is far away from the electron, it would be easy for this electron to sneak out or to go out, and hence lesser energy would be required. While in this other case, when this outer electron is closer to the nucleus, right, your nucleus will have higher attraction towards the electron, and hence greater energy would be required to remove an electron. Correct? So that means if radius is more, ionization enthalpy would be less. And if radius is less, ionization enthalpy is greater. As simple as that. So the trend in ionization potential is reverse the trend in radius. Okay, therefore, across a period from left to right, okay, left to right, we know that atomic size decreases. That means ionization potential would, and down the group, atomic size increases. So ionization potential would
Decrease.
decrease. Ionization potential or ionization enthalpy is same. Please don't get confused by this term. Okay. So okay. So the trend is clear. No problem.
Yes.
Let's quickly look into some question. State the trend in ionization potential across the period. Whenever they say across the period for any trend, it means left to right. So across the period, it
Ionization potential increases across the period.
increases.
And
And down the growth.
decreases down the road.
Okay. Therefore, can you tell me which element will have highest ionization potential? I think it is one of the smallest in the periodic table.
Yes, sir. So is it argon or something like noble gases also count?
Yeah, they do count.
Okay, then it might be any of the noble gases.
So which one?
It depends on which period it is.
In general, in the entire periodic table, which is the smallest element?
Helium.
Helium. Okay, because as you go as you go up, size decreases, and when you go towards the right, the size further decreases. So it's possibly this corner, the top corner of the periodic table, where you find the smallest element, and there lies helium. So I think helium is the one in which it's most difficult to remove electron. For helium and noble gases in general, there are other factors also. One is the size is small. The second factor also is because if you remember, even in this group, like for example, fluorine and neon, last class we were discussing, or chlorine and argon. Among fluorine and neon is slightly bigger because of that electronic repulsion. If you remember last class, I was discussing that. Right? Like left to right, I said the size decreases, but the noble gases are slightly bigger than halogen.
Yes.
And even that is true for the third period. Sodium to chlorine size decreases, but argon is slightly bigger than chlorine. But even these noble gases, though they are slightly bigger in size, their electron configuration is very stable. And hence, because of that extra factor of electronic stability, mostly in N period, noble gases have highest ionization potential because it's most difficult to pull an electron from. Okay, is that clear?
Yes, sir.
So in any period, the highest ionization potential is with the noble gases, and the smallest noble gas is helium. Hence, helium has highest ionization potential. Okay. The lowest ionization potential, I think it would be somewhere in this corner, the biggest element, right?
Is it cesium or francium?
It has to be. It must be cesium or francium. Okay. About this, about that, I told you in last class that francium is rare element and it's rarely found in nature. Because it's even unstable. It's radioactive and it's unstable. So even some traces of francium known never existed for a very long time. They just, yeah.
It's even though it's francium, we say it's cesium.
Yeah, we can say cesium.
Everyone witnessed
Correct.
francium.
Because why this ionization potential increases over a period from left to right?
Because radius decreases and nuclear charge increases.
So left to right, radius decreases and nuclear charge increases. Clear? Next periodic property in our syllabus is electron affinity. It's also known as electron gain enthalpy, but we'll stick to this term, electron affinity. So this is defined as the amount of energy released when an atom in its gaseous state accepts an electron from an anion. So in all periodic properties, you will find that they use the term isolated gaseous atom or gaseous state. Okay, so we are ensuring that the atom is alone and then they are accepting or gaining or releasing electron. Let's suppose one independent atom is there like fluorine. Okay, if fluorine gains an electron, they release some energy. Okay, so because they're becoming stable. So whenever substances become more stable, they lose energy. That's a common trend. if you see here, they have put a minus sign here because thermodynamics says whenever energy is released in any chemical or physical process, released energy gets a negative sign. So negative sign, as per convention, denotes the released energy. Okay. Similarly, the energy which is gained by the system is denoted by a positive sign. Okay. So here the minus sign only implies that energy is getting released. Am I clear?
Yes, sir.
Now suppose there is one atom A which takes an electron. If it gains electron, it becomes an anion, minus charge. And this releases, let's say, minus 100 kilojoule of energy per mole. Another atom B gains electron, becomes B anion, and this releases minus 200 kilojoule of energy per mole. So among these two atoms, which atom has higher electron affinity? Which of the two atoms have higher electron affinity? So here in this case, if A is accepting an electron, it loses, A after accepting an electron loses 100 kilojoule of energy per mole, and while B loses 200 kilojoule of energy per mole. So which has higher electron affinity?
B.
B.
B has higher electron affinity. Okay. Why I am telling you this is sometimes such data are given in your textbook, and I don't want you to get confused. See, when I say a higher electron affinity, it only means that a higher negative value of electron affinity, because electron affinity always have a negative value. Okay. So energy released has a negative value. So that minus sign is only conventionally telling you that energy is getting released. That has got nothing to do with the quantity. Okay, so we don't look at it arithmetically that minus 200 is smaller than minus 100. We just do it, we just take the value for comparison. Make sense?
Yes, sir.
Yes, sir.
Okay. So briefly speaking, higher electron affinity means it has more negative value of electron affinity. Here we have isolated neutral atom A. Okay, A takes an electron and turns into an anion, which has a negative charge, A minus. Okay, and in this process, when A accepted an electron, it became more stable and therefore it released some energy. Energy released is electron affinity of A. Okay, that's it. Okay, let's look into the trend. Again, the trend we'll try to understand logically. Again, for comparison, I have drawn two atoms, one bigger in size and one smaller in size. This is greater radius and this has smaller radius. Okay. Okay. Suppose an atom X gains an electron from someone else. Obviously, it will gain electron from some other atom. So if an atom gains an electron, what is attracting that incoming electron? I mean, like atom consists of electrons and a positive nucleus. Okay. So among them, like the positive nucleus which consists of proton and neutrons, and the electrons among them, which is more interested or which is more excited to gain that electron, incoming electron. Electrons which are already there, they don't have much interest in the incoming electron because they are anyway going to repel it. It's only the nucleus which is excited about the incoming electron, and hence this factor greatly depends on the nuclear attraction. Okay, now let's compare these two atoms. Atom A, the gain electron will reach this orbit, and here this reaches this orbit. Okay, I'm trying to tell this in a layman language for better clarity or understanding so that you could actually relate with this. So now my point is, see, both these atoms gains a incoming electron. Here the electron is at this much distance, and here the incoming electron is at this much distance from the nucleus. Just think logically and tell me which atom is more excited or which nucleus is more excited about the incoming electron.
The
Second one. Okay, basic logic, right? The incoming electron is at a lesser distance and the positive likes negative. So if the electron is at lesser distance, there will be greater excitement. Okay, that means smaller atoms are more excited to gain electron in comparison to larger one. Suppose your parents buy you a gift, like this gift is that incoming electron. Okay, and this. Now, in this case, they say that, okay, you have a gift, but you're going to use it only next year. Probably they get you a mobile phone, but you're only going to use it next year when you go to your 11th. So the mobile phone will stay in their room, a little far away from you. Okay. While in this
Yes, sir.
case, the phone will stay in your room. You can't touch it. You can just see the cover from outside. Okay. In either case, you can't touch it. But where are you more excited? When the phone is in front of you or it is in their cupboard far away from you?
In front of.
So something like that. If the incoming electron are more closer to the nucleus is more excited about it. That was not something scientific at all, and may seem very lame when you study science in higher classes. But it's something good to get started at this level. Okay, so moving further, so the factor which is affecting electron affinity, as I said, is atomic radius and nuclear charge. Okay, so stronger nucleuses with stronger nuclear charge can have greater attraction, and even if size is smaller, it will have greater attraction for the incoming electron. And hence, like with both these factors, if the nuclear charge is big or the if the nuclear charge is big or the atomic radius is less, in both case, electron affinity would be greater. Okay, so we can say that electron affinity is inversely proportional. Okay, so this one I say inversely proportional to atomic radius, means smaller atomic radius will have greater electron affinity, and it is directly proportional to nuclear charge. Clear? Okay. Therefore, now if you understand this logically, I think you don't really need to remember the trend. The trend also becomes quite obvious. So across a period from left to right, electron affinity decreases. Correct? So when you're going from left to right, size is decreasing.
Decrease.
So size is decreasing means electron affinity is increasing. Down the group, size is increasing. So size is increasing means electron affinity is decreasing. Also, the interesting thing to observe here is that ionization potential and electron affinity sound so different from each other but have the same trend. One is about gaining electron, the other one is about losing electron, right?
Yes, sir.
But way it is defined, okay, you need to really understand the definition properly to understand the trend. The way it is defined, the one which has higher ionization potential also has a higher electron gain enthalpy. Okay,
Yes.
let's compare it to let's compare the true property for a smaller atom. In smaller atom, the electrons are close to the nucleus. Hence, it is difficult to lose that. The electrons are close to the nucleus. So, hence, it's more difficult to remove the electron from the atom. Okay, hence, it has higher ionization potential. More energy is required to remove that electron, right? And for the same smaller atom, okay, if an electron comes inside, okay, these electrons are closer to the nucleus. Okay, so therefore this atom is more excited about the incoming electron, and therefore they release more energy in excitement. Okay, so therefore it has more electron affinity also. Am I clear?
Yes.
Yes, sir.
See, when I say a higher ionization potential, it means the value is more positive, like 400 ionization potential is more than 200 ionization potential. But when I say a higher electron affinity, because it's about the energy which is released, by convention, released energy has a negative. So here a higher electron affinity is like minus 400 is higher than minus 200. Clear? Okay, it's now clear that this size has the biggest size and this corner has the smallest size. Smaller size has highest ionization potential and the biggest size has least ionization potential. So therefore least is cesium or francium and highest is helium.
Yes, sir.
Electron affinity also has similar trend like ionization potential. So again here least would be cesium or francium, but we are not interested much in least, we are interested in highest. Which element has highest electron affinity?
Helium.
Is it helium? The trend says it's helium, but if I apply little common sense, I realize that helium has 2 electrons in the outermost cell. It's already stable. It is not interested in any extra electron.
So noble gases don't count in this.
Yeah, so helium, since it's already stable, it doesn't require an extra electron. And since it does not require an extra electron, it will never release energy out of excitement if it gains an electron. It will rather be more disturbed, like, why are you giving me an electron? Okay, so it has no interest in taking that electron. So the trend which you learn for electron affinity is applicable only till halogens. Am I
Yes.
clear?
Is the less electron.
Is that fine?
Yes, sir.
Now you think you know the answer. What's the correct answer?
Fluorine.
Fluorine. Which unfortunately is a wrong answer again. Okay, here in electron affinity, it's always the period 3 element, mostly this side, has greater electron affinity than period 2 element. Okay, this is something which is a very important concept in 11th standard. They will explain in detail why it happens, but always you can remember with respect to their respective member in the same group in period 2, period 3 elements have higher electron affinity. So chlorine has higher affinity compared to fluorine. Sulfur has higher electron affinity compared to oxygen. Phosphorus has higher electron affinity compared to nitrogen. Silica has higher electron affinity compared to carbon. But so that is against our trend, right? The trend can be seen after period 3, means bromine has lesser than chlorine, iodine has lesser than bromine, astatine has lesser than iodine, chlorine has more than fluorine. Is that clear?
Yes, sir. But why is that?
So it means that fluorine to chlorine it increases and then decreases, 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 decreases. Oxygen to sulfur it increases and then it decreases, decreases, decreases. Nitrogen to phosphorus it increases and then it decreases, decreases, decreases. Am I clear? Okay.
Yes, sir.
Do you want to know why?
Yes, sir.
Okay.
Yes, sir.
See, the period 2 elements, okay, they have only 2 cells. This is nucleus, they have only 2 cells. And in second cell, suppose this is fluorine having 7 electron. And like, so even chlorine has 1, 2, 3 periods. In chlorine, in the third period, you have 7 electron. Now, both these atoms are excited about gaining 1 electron. So this is fluorine and chlorine. Both these atoms are excited about gaining an electron. Okay, fluorine, if it gains 1 electron, will have 8 electron in the outermost cell, and chlorine also, on gaining an electron, will have a stable electronic configuration with 8 electron in the outermost cell. So both are excited to really release that energy, okay, when they gain an electron. If we look as per the trend in the size, fluorine is smaller than chlorine. Okay, therefore it looks like fluorine will release more energy being smaller in size. But just in this special case, in comparison between period 2 and period 3 element, another factor kicks in. Okay, chemistry always have a lot of exceptions because 1 or 2 parameters which we mostly ignore because it's not applicable to that extent in general. But here, this parameter is also important. What's the parameter? The factor which will the other factor which becomes significant here is the electronic repulsion. Okay, so these electrons, pre-existing electrons, okay, have repulsion for the incoming electron. So though the nucleus is trying to pull it, the electronic repulsion are significant because there's less space. It's small in size, right? So it's a small house. There are already 7 electrons. So the incoming electron feels greater repulsion from these 7 electrons. While in case of chlorine, that also has 7 electrons, but these 7 electrons are a little bit more distributed because of a bigger size. In fact, you learn also in higher classes that from period 2 to period 3, when you go down, the increment in size is a lot. Okay. So there's a huge gap between, like, there's a bigger difference in the size between period 2 and period 3. Okay. In fact, that gap is more than the gap between 3 and 4, and 4 and 5. And you will be surprised to know that, 5 and 6, and you will be surprised to know that 6 and 7 have technically no gap. I mean to say that osmium and this element over here are almost same in size. Here, coming back, see what happens. Simple. in comparison to period 2 and period 3, period 3 has higher electron affinity because though they have bigger size, electronic repulsions are less for the incoming electron. Am I clear? This is explanation just for your understanding.
Yes, sir.
Yes, sir.
Okay. So period 3 element have higher electron affinity, and they just directly ask you which element has highest electron affinity. So it's in one of this corner, but it's not helium and it's not fluorine. It is chlorine. Clear?
Yes, sir.
Yes.
So I'll mark this here. Highest electron affinity. Okay. So the first question here is which has highest electron affinity? It's fluorine or neon? Which element has highest electron affinity? It's fluorine or neon?
Sir, fluorine.
This is the question.
Oh, okay. Thought it was anything. Let's see.
So which has highest electron affinity? Fluorine or neon?
Fluorine.
Fluorine has highest electron affinity because we said that the halogen family has higher electron affinity in comparison to noble gases. In fact, noble gases have least electron affinity. They're highly stable. So though they are on the extreme right of the periodic table, they have the least electron affinity in the periodic table. So sometime if they ask you which element has zero electron affinity, people are searching on the left side, okay, of the periodic table. Right. So a lot of times this also becomes confusing. If a question comes in exam, in a given period, which group has least electron affinity? We are searching here. Okay, they have the least electron affinity. Okay, but actually the least or zero electron affinity would be here. Okay, that's the exception. Okay, moving to the next question. Which elements has the highest ionization potential? Okay, the smallest will have highest ionization potential.
Hydrogen. Sorry, helium.
Helium.
Yeah.
It's in the top right corner.
Yeah.
The most electronegative element from the following element is, oh, we haven't done electronegativity, so we'll leave that. We'll see that in the next part. Electronegativity. This is another periodic property. Electron affinity and ionization potential, the two property which we did before this, are basically energy terms, means they are measured in energy. Okay. This is not an energy term. This is not like some energy released, given, or taken. This is more about tendency. Okay. So electronegativity means the tendency of an atom to attract shared pair of electron towards itself when combined in a compound. All right. So suppose we have a bond, a chemical bond between two elements A and B. Okay. How do A and B form a chemical covalent bond? I think by sharing of electron.
Yes.
Okay. Here I have kept this shared pair of electron right in between A and B. Look like it is exactly in the center. But are you sure that these shared pair of electron are always in the center or right between the two? Is it possible that these shared pair of electrons are more closer to one element? What is your opinion on this? What do you think? The shared electron, both are giving 1, 1, so let's keep it in the center. Or is it that one can dictate terms and say, no, we are going to keep the shared pair of, I'm going to keep the shared pair of electron towards myself, more closer to
I
me.
think that's possible, right?
That is possible. See, actually, this is the most likely situation whenever a chemical bond, a covalent bond is formed between two elements. Okay. So whenever two elements combine to form a covalent bond, two different elements, obviously, when they combine to form a covalent bond, sorry, one of the two elements dictates term and try to pull the shared pair of electron closer to itself. This tendency of an atom to pull the shared pair of electron when it is in a chemical bond towards itself is known as electronegativity. Okay. So a more electronegative element will more likely to pull the shared pair of electron towards itself. Am I clear? So it is not about complete gain of electron, that I have completely gained your electron, hence I am releasing energy. This is just about the tendency that if you combine with me, I will pull the electron towards myself. Okay. So electronegativity means the tendency of an atom to attract the shared pair of electron to itself when combined in a compound. Yeah.
Yes, sir.
Okay. Now, what is the trend? See, the trends are very similar to electron affinity and ionization potential. Just like smaller atoms would be more excited to gain electron, even smaller atoms would have greater support from the nucleus to pull the electron towards itself, right? So we can just say that electronegativity is inversely proportional to atomic size, and it is directly proportional to the nuclear charge. Okay, so if we go to this periodic table over here, since the trend is similar to electron affinity and even for electronegativity, I think the most electronegative element will also be in this corner, right? Which element has highest electronegativity? Even in this case, we can discount the noble, right?
Yes, sir.
Because they
Yes,
are
sir.
not. First of all, they won't form chemical bonds. So where is the question of pulling the electron towards themselves? So it has to be something between the among the halogens. Now, see, in this case, electron affinity, it is just trying to pull the shared pair of electron closer to itself. So it's not even completely pulling the electron inside. And since it's not completely pulling the electron inside, the electronic repulsion factor is not a major issue here, right? I hope you understand my point.
Yes, sir.
Therefore, for
Yes.
electronegativity, we can say that fluorine has highest electronegativity. Am I clear? Because here it's
Yes,
just
sir.
pulling the shared electron more closer to itself. It's not about completely taking it in that there's electronic repulsion. Correct. So therefore we understand now very important points to recap is helium has highest ionization potential, fluorine has highest electronegativity, chlorine has highest electron gain enthalpy or electron affinity. Clear? Please remember these three names. I hope that's fine.
Yes.
Yes, sir.
Okay. So that was all about electronegativity. So inversely proportional to atomic size and directly proportional to nuclear charge. Trends, therefore, is same as ionization potential and electron affinity. Across a period from left to right, electronegativity increases, and down the group, electronegativity decreases. No problem with this?
No, sir.
Okay,
No, sir.
super. Okay, the next property is metallic and non-metallic characteristic. Okay, metallic characteristic means the ease of losing an electron. Okay, so an atom is said to be a metal if loses one or more electron. So if metal generally loses an electron and it becomes a cation. Okay, so if M loses one electron, it becomes M plus ion. Okay. Similarly, non-metallic characteristic is when an atom gains an electron, one or more electron to become an anion. Okay. Next is what are the factors affecting metallic and non-metallic characteristic? It depends on atomic rays and ionization potential. So smaller atoms will be more non-metallic in nature because they are less likely to lose electron and they are more likely to gain electron. Okay, therefore all the non-metals lies on the right side of the periodic table, right? And also ionization potential. So the bigger atoms have lesser ionization potential, and it's easier to pull electron from them. So therefore, the metals lie on the left side of the periodic table. Clear? Metal present on left side of the periodic table have large atomic radius and low ionization potential value and tends to lose electron. Metals are good reducing agent. Okay, remember this. They're good reducing agent because they can give electron. Reducing agents are electron donors. Yeah,
So, how is it reducing agent when it loses electron?
yeah. It's loss of electron is known as oxidation.
Yes.
But when you're getting oxidized, you're helping someone else get reduced.
Oh, okay.
Okay. So whatever you're giving your electron to, that substance or that element is getting reduced.
Okay.
So that way.
Okay. So, when we say the reducing agent,
Mhm.
and while saying reducing agent, when we say rather than the gain electron, they help others gain electron. Can we say that?
Yeah. Reducing agent don't gain electron. They rather lose electron and they help other gain electron.
Okay.
Reducing agents is it's an agent. Like a travel agent gives you a travel ticket. Okay, so a reducing agent is giving you electrons. It's an agent. It's helping other. It's not the travel agent themselves don't travel. They help you travel.
Yes, sir.
Moving further to non-metals. Non-metals present on the right side of the periodic table have small atomic radius and have high ionization potential value, and they tend to gain electron. Okay, all the non-metals, they are small in size, they have very high ionization potential, so they're not losing electron, and they have high electron affinity, so therefore they tend to gain electron rather. Non-metals, since they are gaining electron, they can help other get oxidized, and hence they are good oxidizing agent. All right, let's get into the trends. Again, pretty simple. Across a period from left to right. Okay, when you go from left to right in any period, metallic characteristic decreases. That's why you see that in like groups, towards the left side you have more metals, and the group towards the right side you have more non-metals. Across a period from left to right, like for any period, for example, sodium, magnesium, aluminium, silica, okay, phosphorus, sulfur, chlorine, argon. This is period 3. So in period 3, this side you have all metals, then you have a metalloid, and here you have all non-metals.
Yes, sir.
Okay, so that means in period 3, when you're going from left, like in any period, when you go from left to right, the metallic characteristic decreases. Means left side you have more metals and right side you have non-metals. And if the metallic characteristic decreases, certainly the non-metallic characteristic would increase. Okay, going down the group. Okay, down the group, metallic characteristic increases. Uh, to understand this factor, okay, to understand this factor better, the best example of the group which you can use is the carbon family, means group 14. In group 14, first element is carbon. This is a non-metal. After carbon, we have silica. This is a metalloid, or it is a intermediate between non-metal and metal. Then germanium. Okay, that is also a metalloid. It's in between metal and non-metal. And then you further go down. You have tin and lead. Tin and lead, we are familiar, they are metals. So can you see in the same groups there is so much of variation? Top is a non-metal, then metalloid, and then metals. So that this group is a good example to explain how the metallic characteristic increases as you go down the group. Correct?
Yes, sir.
So the metallic characteristic increases when you go down and left. So this corner is where you see more metals. In fact, this is all metals. And non-metallic characteristic increases when you go up and towards the right. So this corner is where you see the non-metals. Okay, non-metals is actually a smaller family compared to metals. But among metals also, the metals on this side is more reactive metal. In fact, these metals here in the center, the transition metals, you'll find that a lot of them are non-reactive metals. Like this gold, gold is non-reactive. That's why people wear it in form of jewelries, because it doesn't react with your skin. Same can be said for silver or platinum. So all these non-reactive metals are somewhere in between. Yeah.
Yes, sir.
Just a final last table to summarize everything. Okay, this is all we studied till now. So just a final recap on this. Atomic size across the period, left to right, decreases.
Decreases.
And down the group, atomic size
Increases.
increases. Metallic nature follows the same trend as atomic size. So even
Yes.
that decreases and down the group increases. Okay, if you look at the other four properties, non-metallic characteristic, ionization potential, electron affinity, and electronegativity, they have trends opposite to the trend in the atomic size. Okay, this just in
Yes.
for quick like recap, like if you forget an exam and if you don't have enough patience to think in detail, so you can just remember that see, size strength is something which is easy to remember. It decreases, increases. It decreases down the like across the period, increases down the group. And the others like non-metallic properties, ionization potential, electron affinity, and electron gain affinity, they all have opposite trend to atomic size. Clear?
Yes, sir.
Okay. So we can just go through some questions quickly. Atomic size of an element is 15. State the period to which it belongs. Atomic number of an element is 15. State the period to which it belongs. I think for that we can write the electronic configuration. So it's 2, 8, and 5. So which period does this element belong to?
Period 3, I guess. 2 or 3.
Period 3. There are 3 cells, so period 3. The group to which it belongs. Do you know how many valence electrons are there?
5.
5.
5. Is it a metal or a non-metal?
Non-metal.
Non-metal. Okay, now let's come to the second question, the group to which it belongs. If you remember, I said, if you have one valence electron, you are in group 1. If you have two valence electron or if the element has two valence electron, it is in group 2. If element has three valence electron, it is in group 13. Four valence electron, it is in group 14. Okay, because see between 2 and 12, that's transition metal. 5 valence electron, it is in group 15. 6 valence electron, this is in group 16. And then 17 and 18. Okay. So if
Yes.
valence electron is 5, to which group it belongs to?
15.
Group 15. That's it. Clear?
Yes, sir.
Yes.
Okay. Let's see the next type of question. Arrange the following element as per the guideline. Sodium, chlorine, magnesium, phosphorus. Decreasing order of atomic size.
From increasing to decreasing.
Decreasing order, yeah, bigger to smaller.
Sodium,
Okay.
magnesium,
Okay.
phosphorus, then
Increasing order of electron affinity.
first is lithium,
Okay.
then carbon,
Okay.
then fluorine, and then neon.
No, that's not neon. That's nitrogen.
Oh, yeah. Nitrogen, then fluorine.
So again, left to right, basically.
Yes.
Okay. Increasing electronegativity. Fluorine, iodine, bromine, and chlorine. All these are members of group 17, halogen family.
Yes.
So increasing electronegativity, down the group size increases.
Yes.
So electronegativity would decrease.
Yes.
Electronegativity maximum would be fluorine, the
Then
smallest.
fluorine,
Yes,
bromine, and iodine.
bromine and then iodine. Okay, so this goes fluorine, fluorine, bromine, iodine. Fluorine, aluminium, magnesium, sulfur. Increasing order of potential, ionization potential.
So is it like from the period?
Yeah, increasing order of ionization potential. So left to right ionization, but it is they're all in the same period, right?
Yes.
So in the same period, left to right ionization potential.
First is magnesium.
First is magnesium. So ionization potential left right increases. So
Magnesium is lesser than aluminium.
Mhm.
Aluminium is lesser than sulfur is lesser than chlorine.
I hope the others also understood this. No problem.
Yes, sir.
The elements A would have lesser, higher electron affinity than B. So in period 3, element A is on the right of element B.
Has higher electron.
It's on the right side. So right side will have higher. Okay, right side is that. Yeah, right side has higher.
Yes, sir.
Nuclear charge of element B would be
Less than element.
less. Okay, so I'll write B here and A here for better understanding. So B has less. The element A would probably have a smaller or larger atomic size than B.
Smaller.
Okay. The element B would probably have lower, higher ionization potential than A.
Lower.
Lower. If an element C has a lower electron negativity and ionization potential, it would have more tendency to. If an element C, okay.
Lose electron. Like if it has low electron negativity, loses.
So it has low electronegativity and ionization potential. In both cases, it is more likely to lose electron
Yes.
because it's easier to remove an electron. Okay, Anvisha and Maria, you understood this?
Yes, sir.
Okay. You have 7 questions. The most electronegative element among the above you see a table in which some elements have their original symbol while others are represented by random variables.
Yes, sir. Electronegative element. So electronegativity increases across a period and decreases down a loop, right?
Yes.
So the most electronegative element, uh,
It's there in the top right corner.
but halogens, is it included in electronegativity?
Halogens are included in electronegativity.
Oh,
Noble,
okay.
noble gases
Noble
are not.
gases are not. Okay.
So
Yeah,
can answer.
let it try.
Right.
So it is Z, right?
Yes, sir.
Okay.
So next one also.
Yeah, all 7. Valence electron in element K and its valency. Valence electron in K
6 valence electrons.
and valency.
Valency will be the minus. So 2 minus.
-2. Okay.
Yeah.
The most reactive element of group 1.
Of group 1, R.
R is the most reactive. See, I did not discuss much about reactivity, but as far as group 1 goes, in group 1, as you go down, it's easier to lose the electron. So the reactivity increases.
Yes.
Okay, so that's R. From group 2, the least ionization in energy.
Group 2. So is it C?
So it is C. So we have to answer only from the elements given in the table, shown in the table.
Yes, sir.
Okay, though there are periods 5, 6, and 7 below that, we don't write answer according to that.
Yes, sir.
Okay, the element from period 3 with smallest atomic size.
From period 3, atomic size. The atomic size decreases across a period, right?
Yes.
Okay, and it increases. So
Smallest size.
A.
No, left side.
No, sorry. Why?
Think again.
No, it's Q. Is it Q? Yeah, because
In any period, the halogens are the smallest.
yeah.
Okay, so you need to keep all those rules in your head. So it's
Yes, sir,
Q.
yes. Q.
Okay, a noble gas of period 4.
P.
That's T. Element in group 16 with highest electron affinity.
Electron affinity. So uh
Sure.
Mhm.
Is it J or K?
Yeah, that's a good question.
Oh, yeah, you explained it. Yeah, never mind. So it's K?
It is K, yeah. It's always from period 3.
Okay. So period 3, it has highest electron affinity. Like,
Yes, period 3 members will always have highest electron affinity in their respective group.
yes, sir. Yes,
And
sir.
after that, the trend is normal, like when you go further down.
Yes, sir.
Next, Maria, would you like to answer a few questions? Select the correct answer. Element with atomic number 19 will most likely combine chemically with elements whose atomic number is.
Seventeen.
17. Because 19 means 2881.
Yeah, and 17 is 288. I mean, yeah, 287.
7. So it will combine with 17. Okay. This is a metal. Metal don't react with metal. This is a metal. It doesn't react. This is a noble gas. So it only reacts with a non-metal. Identify the term in each of the following. The tendency of an atom to attract electron to itself when combined in a compound.
Electronegativity.
The electron present in the outermost shell of an atom.
Valence electron.
Fill in the gap with the greater than or less than sign. Ionization potential of potassium is less than that of sodium.
Greater.
Check again.
Ionization potential, right?
No. Potassium.
It increases. Oh, no, no. Not its phosphorus, I don't see. Decreases.
Down the group size increases, so the potential decreases. So
What?
potassium is less than that of sodium. The electronegativity of iodine is that of chlorine.
Less.
So iodine has lesser electronegativity than chlorine because down the group electronegativity.
Oh, never mind. Okay.
Down the group it decreases. Chlorine
Yeah.
is most electronegative element. Okay, so always in the periodic table, you remember the highest are in this corner and the least are in this corner. Okay, so chlorine, bromine, iodine. It decreases. It decreases this way, it decreases down. Clear?
Yes, sir.
Okay, I hope you got an understanding what's there in this chapter and what are required. So keep practicing more and more questions.
Yes, sir.
Okay, I think that's then fine for today. We'll continue again in the next session. Thank you and bye for now.
Bye, and thank you.
Bye.